Math back. AMC 12, 2021B fall. This is going to be problem number 14. Suppose that P of Z, Q of Z, and R of Z are polynomials with real coefficients, having degrees 2, 3, and 6 respectively, and constant terms 1, 2, and 3 respectively. Let n be the number of distinct complex numbers z that satisfy the equation P of Z times Q of Z equals R of Z. What is the minimum possible value of n? So this problem's pretty tricky, but really what it comes down to is a pretty basic understanding of what's called the fundamental theorem of algebra. The fundamental theorem of algebra says that a polynomial of degree n must have n complex roots, right? Now, some of those roots may be repeats, right? In which case we would say, that we would have like a root having a multiplicity greater than one. Like, so for example, when you have a quadratic that passes through the origin, where the vertex is on the origin, right? You would say that the only root is 0, but technically you would say that it has two roots that are both equal to 0. So, right? And notice how, like in the problem, they say let n be the number of distinct complex values, right? So they specifically use the word distinct because, some of the roots could be repeats, right? So the first thing we'd want to ask ourselves is like, well, is 0 possible? Well, the answer is no, because you can't have a real polynomial with 0 roots. It's just not possible, right? And especially because we're multiplying. Remember, like, so this polynomial has degree 6, and this polynomial has degree 2, and this one has degree 3, which means that when you multiply these together, you'll create a polynomial of degree 5. So here you have a polynomial of degree 5, and here you have a polynomial of degree 6. So ultimately, this equation will end up as a polynomial of degree 6. So it has to have 6 roots. So the question just becomes how many distinct roots. So can we come up with a situation in which we would only have one distinct root? And the answer is yes, and it's actually pretty simple. So let's let P of Z be equal to Z squared plus 1, right? So that way we have a polynomial of degree 2 with real constant term 1, right? Let's let Q of Z equal Z cubed plus 2. Right? Yeah, Z cubed plus 2, right? Because then that's going to be a polynomial of degree 3 with constant term 2. And then let's let R be the polynomial Z minus 1 to the power 6 plus Z squared plus 1 Z cubed plus 2, right? So basically the product P of Z plus Q of Z, right? So now if we solve this equation here, right? P of Z times Q of Z is equal to R of Z, right? Then we're going to have Z squared plus 1 Z cubed plus 2 is equal to Z minus 1 to the power 6 plus Z squared plus 1 Z cubed plus 2, right? And then notice how, sorry, these are supposed to be 2s. Notice how then like these will this will cancel with this. So you're left with like 0 equals Z minus 1 to the power 6. Oh, and notice how this polynomial here will have constant term 6. We'll have constant term 3 because you'll have like 1 times 2 will make 2. And then you're going to have minus 1 to the power 6, which is 1. So you have 1 plus 2 is 3. So don't forget about the fact that this has to have a constant term of 3, right? So we get 0 equals Z minus 1 to the 6, which means Z minus 1 is 0, which means Z is 1. So this will basically have one root with multiplicity 6, but it's still one distinct complex root. So we found a situation in which we would have one distinct complex root, right? So therefore the answer would be B1. So it's kind of like this is more of a conceptual problem, I think, than really a mathematical. Like, it's like it's testing the concept of fundamental theorem of algebra, complex roots, and the fact that like you know, a polynomial of degree n must have n complex roots, but some of those roots can be repeats, right? So they're not distinct complex roots. So the key word here was the fact that they used the word distinct, right? So pretty tricky problem, but overall not too bad. Okay, in my next video, I will be going over problem 16. All right, I will see you there.